for organizing this. Thank you, Leah, for organizing the seminar and for inviting me. I'm Keyon. I'm a postdoc at Harvard as part of the Harvard Data Science Initiative. And today I'll be presenting work which will appear later this year in NeurIPS. This is work with Justin Chen, John Kleinberg, Sendhil Mullainathan, and Ashesh Ramachan. So let's see. We have I'll leave some time at the end for questions, but also if you have any questions during the talk, feel free to just post them in the chat. I'll be hopefully taking a look at the chat. So I want to start by talking about how do we go back? Yeah, I want to start by talking about large language models. We have a lot of large language models out there. We almost have too many to count, but there's a conundrum, and it's what motivates a lot of the things I've been thinking about lately and what I'll be talking about today. So let's start with the obvious, which is that these large language models do amazing things on a bunch of metrics. They can pass AP exams in English or math SATs or perform in coding competitions and get high scores. And it's not just the level of these metrics that's impressive, it's also the rate of progress we've seen in the past couple of years. And it's not just the metrics. The metrics are capturing something real. I think, each one of us in the Zoom call, I'm sure, has had an experience where we've played with a large language model and we've seen it do something truly amazing. Here's an example I like from the Sparks of AGI paper about infinitely many primes. And, I think it's easy to be cynical about large language models, and perhaps we ought to be cynical about research conducted through press releases. But at the same time, it's undeniable that these large language models are doing something incredibly impressive. And especially I don't think any of us could have imagined 5 years ago or 10 years ago that this is where we'd be at this point in time. At the same time, I'm sure we've each had experiences where we've used a large language model and had to do something truly amazing, and then turn around and use it again and have it do something truly goofy. So here's an example that I like quite a bit, where if you ask GPT-4, if you give it a few travel itineraries for train, car, and metro, along with costs and travel times, and ask GPT-4 which mode of transportation to take, GPT-4 will start by saying, to make a decision, we need to calculate the cost per minute of each mode of transportation. And so it gets you the cost per minute of train rides, car rides, and metros, and says that, well, look, the train has the lowest cost per minute. You're getting the best deal on the train, so you should take the 395-minute train instead of the metro, which is about 5 times as fast and only costs $3 more, just because the train is a better deal. So I think this is hilarious because if the train were twice as long, if it were 800 minutes, it would say that that's an even better deal. We sort of have this trifecta of amazing metrics, and also incredible examples, but some truly goofy performance. And this raises the question, which is how can we trust these metrics if they don't seem to be capturing the full spectrum of how these large language models perform? And so this is a new problem specifically for large language models, but we've actually been here before. We've had the combination of impressive metrics, incredible examples, and really goofy examples. So to see that, let's go back in time, way back in time to the good old days of supervised learning. In supervised learning, we had metrics, we had ImageNet, we've had many other classification data sets. And it's not only the metrics. We've had incredible examples where image classifiers could do things that humans couldn't do, such as identifying whether two pigs are the same. I love this example. And it's apparently also a useful example because people could use it apparently in farming and agriculture. But at the same time that we've had these impressive examples in supervised learning, we had truly goofy examples. So here I'll just highlight, one adversarial example with pigs. The same model that can tell whether two pigs are the same thinks that if you add a little bit of adversarially chosen noise to a picture of a pig, that it's an airliner. So, again, in both LLMs and supervised learning, we've had this trifecta of impressive metrics, great examples, and truly mind-boggling examples. But it feels like we have a handle on the problem for supervised learning. It feels like we at least understand how to evaluate and understand supervised learning models, and know what their pathologies are. And so, that might give us some optimism. Does that mean that we can sort of use the same approach to trust LLMs more? Well, to answer that, we should go back and see how we've actually thought about supervised learning and frameworks for evaluation. So in supervised learning, we have a function f, maybe it's a binary classifier, that takes some input x and transforms it into an output y. And the crucial question for evaluation in supervised learning is asking, where will the classifier be used? And a lot of times in supervised learning, this answer is very straightforward. Supervised learning methods are developed for one specific task. And so typically there's a narrow set of instances in which we can use the classifier. So in the case of pigs, if we want to use a machine learning classifier to tell whether two pigs are the same, we wouldn't use that classifier to do arbitrary other image things. We would use it to tell which two pigs are the same. And so we have guarantees that if we identify distributions that capture how a model will be used and evaluate that model on a distribution of instances that is roughly similar to that sample, then we have guarantees on how similar the performance on our evaluation will be and how the performance when we deploy it will be. And a lot of the pathologies with supervised learning happens when these two distributions are different, such as distribution shifts and adversarial examples. These are examples where the deployment distribution is not different, is not the same as the evaluation distribution. So now looking at large language models, we have a similar setup where we have a function that goes from an input to an output. Here, the input is a textual prompt. Maybe the output y is an answer. And so the crucial question for evaluation is, where will a large language model be used? And unlike supervised learning, there's not a straightforward answer. Large language models are general purpose, even though they're pre-trained on one kind of narrow task, which is predicting the set of next tokens from articles on the internet or other articles. They're capable of far more, and people will be using them for far more. You can use the same model as a chatbot or to generate code or even for medical advice or to answer proofs that rhymes. And so because the same model can be used for all these different kinds of tasks and instances, it's unclear what distribution people will actually be using to deploy large language models to. So in other words, these large language models are general purpose technologies that can't be captured by single evaluation distributions. So there's something that the evaluation metrics aren't capturing. And unlike in the case of supervised learning, evaluation metrics just aren't good proxies for how people will use LLMs in practice. While they can tell us about narrowly defined deployment distributions, no single predefined distribution of instances can capture the way we actually use LLMs. So in this sense, evaluation is the major problem of LLMs for not only deciding which LLMs are effective, but also for improving them. How can we improve the real-world performance of LLMs if we don't have good evaluation proxies for how they're used in practice? So this is a question I've been thinking about recently, and I think that there are a lot of different approaches for coming to more, satisfying conclusions to this problem. And today I'm going to talk to you about one such approach. And this approach assumes that there's some true world model, a function f star that dictates which sequences are valid. And I'll define this all more formally in a bit. But the basic idea is that if an LLM f is equal to this true world model, then the distribution of instances won't matter for evaluation. So learning the true function is in some sense the only true distribution-free way to evaluate, because no matter what distribution we evaluate against, the model will capture the true structure, the true language. And so that means it has understood the world. So the question I'm going to cover in this talk is, how do we know if an LLM has understood the world that governs the sequences that it is trained on? And so to make this a little bit more concrete, let me talk about a paper that you may have seen. It's a very nice paper from last year that considers the board game Othello. So for those of you who are unfamiliar, Othello is a board game that involves an 8x8 grid, and two players take turns placing a single tile at different spots of the grid. And so the rules are slightly, so the kinds of tiles that are allowed depends on the current board, like where you place the tile depends on what the board looks like. And the rules that govern Othello are a little bit more complex than the rules that govern other games like checkers or chess. And so what this paper did is it took a bunch of games from Othello and tokenized them into sequences, where each token in the sequence corresponded to a move that a player made during a game. So sort of serialized games into these sequences of just numbers between 1 and 64 corresponding to the position of the tile that was placed at each point in time. And then they trained transformers on these sequences just to predict next tokens. And so they found that transformers trained on next token prediction did very well out of sample, that most of the times they predicted legal moves. And that led to the question, has this transformer understood the rules of Othello? Which would actually be, amazingly impressive if without seeing any kind of board information, just the states, has it understood that there is a board and that its predictions must obey this idea of a board. And so this is sort of there's a nice beauty about using the controlled environment of Othello for evaluating a world model because we know what the true rules are, even if the transformer may or may not know it, and it gives us a way to evaluate. And so this paper proposed some, very, very, very interesting and fascinating initial analyses. And the goal of this paper I'm going to talk to you about today is asking the question, how could we tell if an LLM has understood the world model and does this happen? So we're going to formalize this question based on results from language theory, and then based on these results in this question, derive metrics for evaluating world models. So this is what I'm going to be talking about today. I want to start by covering some preliminaries. So throughout this talk, I am going to use generative model to refer to a function M that takes as input some sequence over some dictionary over some alphabet sigma and returns a probability distribution over next tokens over that alphabet. So this generative model, you can think of it as a transformer or something. It takes some prefix and then just provides some probability distribution over all possible next tokens. And so by defining it this way, our generative model is implementation agnostic. It can be any sequence model, be it an RNN, a transformer, even some non-parametric sequence model, such as a bigram model. And so with this definition of generative model, I'm going to assume that there is some true world model which can be modeled as a DFA. So there's going to be, and so by structure here, I mean that there's going to be some set of true states and transition rules that govern which transitions are legal between states. And we're going to ask what it means for the generative model to recover to recover the true world model. And so there are a few ways that we can ask this question. One way that is quite interesting, but we don't take, is to try to assess the inner workings of the model by looking at the representations of something like a transformer. And I think this is an interesting approach, although it's not the approach we take for a couple of reasons. One is that there is an isomorphism problem, and that you can have two identical DFAs that have very different looking representations. So here's one where the game tic-tac-toe, it is isomorphic to a magic square-like game called Pick 15, although the representations of each state look actually quite different. And moreover, representations, just looking at a model's representation, is an indirect way of telling you about how a model behaves. So it could be the case that a model's representation maybe looks just like an Othello board, but it's not actually predicting moves that reflect the structure of Othello boards, and that in and of itself would be interesting. So instead, we're interested in testing the behavior of the model and seeing if its behavior obeys some kind of structure that is described by the DFA. So this gives a very natural DFA recovery, where we say that a generative model M recovers a DFA if all prefixes that are if all sequences that are accepted in the DFA are also valid in the generative model. So the generative model operates at the string level, DFAs operate at the state level, and so we just define this by saying for all states, for any prefix that leads to that state in the DFA, the valid suffixes in the DFA have to be identical to the valid suffixes in the generative model. And I want to point out that this relies on some notion of validity for generative models. And where this definition means that generative model has to accept some suffixes and not accept some other suffixes. So one natural definition for this is that a model accepts the suffix if it assigns all tokens in that suffix probability above 0. Now, that definition is natural, but in practice, language models are so heavily regularized that they'll assign every suffix, every token in a string probability above 0. So in practice, we can consider other ways of defining validity. In this talk, I'm going to use different probability thresholds like 0.01 or 1 times 10 to the negative 3 or 4. And we'll vary these thresholds and sort of see how that changes the behavior of the model. So with this definition of what it means to recover the DFA, there is a result that a generative model recovers the DFA if and only if it satisfies exact next token prediction. And what it means to satisfy exact next token prediction is written out here. It essentially means that for all possible prefixes that lead to a state, the model's support of valid next tokens from that state have to be valid next tokens in the DFA. And so in other words, if a generative model always knows the exact set of next tokens that are legal for any prefix, then it implies that it has recovered the DFA exactly. And this is a nice result in that we can think about, sort of this may be one way to think about the power of large language models. They're just trained to predict next tokens. And so if they can do this perfectly, it might imply some actual hope at recovering the true DFA. And this result suggests a simple and intuitive test for assessing whether a generative model has actually recovered the DFA. And this test is based upon looking at its next token predictions. So the test is as follows. We can take a prefix. So in the context of Othello, maybe the prefix would just be the first 20 or 30 moves of a game, the beginning of some Othello game. We can then use the true known DFA to calculate the state that is implied by that prefix. Given that DFA, and here the state is just the board, we can calculate the valid next tokens from that state. So in the context of Othello, the valid next tokens are the set of valid next moves. And then so because we know the true set of valid next tokens, we can then take this prefix that we had, feed it to our generative model, and see what next tokens it thinks are valid. And then we can say that we can look at the performance of that model by comparing its predicted next token or next tokens to the true set of valid next tokens. And if it has recovered them exactly, it suggests that it's done a good job of learning these next tokens. And so this is a nice test. It's intuitive, but you may ask, how informative is this test exactly? And so to answer that, I'll walk through a simple example that we call cumulative connect for. And it sort of works like the game Connect 4. We are going to imagine there's a sort of vertical grid with n rows and 7 columns. And players are going to take turns dropping disks in one of the 7 columns. And then when you drop a disk in the column, it goes all the way to the bottom. And so, like true Connect 4, you can drop a disk in any column that isn't filled. But the only difference between this and regular Connect 4 is that we're going to assume, just for simplicity, that players will continue playing even after they have 4 in a row. So really, they're just taking turns dropping disks into one of 7 columns. And so now, just note that this game has a true, the DFA of this game corresponds to a DFA where the states are the different boards, and the transition rules correspond to which of the columns are filled in each board. So, I'm going to tell you that For a large board, for n equals 1,000, I have an algorithm that passes the next token test 99% of the time. And so that means that for 99% of the different sequences, its exact predictions of the valid next moves is equal to the exact same set of valid next moves. And so this may seem like, quite an informative algorithm that has captured something about the world, but here's the algorithm. Just always predict all next tokens are valid. For every sequence, just say, I could be column 1, 2, 3, 4, 5, 6, or 7, and just make that the prediction for every possible state. Now, of course, this algorithm has captured nothing about the true world. It's always making the same prediction, but it's performing very, very well at the next token test. And the reason why is that there are many states that have the same possible next tokens. So here's another board to the right of the original board. These two boards are pretty different. They imply different games. But if you just squint and just ask what are the same sets of possible next tokens, they're exactly the same. Both of states have allow to, but both states allow all possible next tokens. And so, this test doesn't differentiate between many states, especially if many states share the same possible sets of next tokens. So, to summarize, while doing perfectly at next token prediction implies exact world model recovery, it's also the case that doing nearly perfectly doesn't mean much. And this actually relates to a classic result from language theory, the Myhill-Nerode theorem, which states that any two states in a minimal DFA must have suffixes that differentiate between the two states. So in other words, there must be a suffix that's legal in one state and illegal in the other state. Now, the key, though, is that these differentiating suffixes can be very long. They might be one token or they might be much longer. So if you look at, these two boards, there is, of course, some differentiating suffix that exists in one board, not the other. So for example, if you just consider putting four tiles in the first column, you can do that for the board on the left, but you can't put 4 columns in the first column in the board on the right. So once you get out to 4 tokens here, that's when these states really start to differentiate. And it's also longer than 4 columns. There are sequences of 10 tiles or 15 tiles that still admit the same set of valid next tokens for both of these boards. So this theorem gives rise to something that we call the Myhill-Nerode boundary between two states, which is the set of minimal suffixes that are accepted starting from one state, but not from the other. And so we've tried to depict it in this figure to the right, perhaps somewhat confusingly. This figure is showing two different states, and you can imagine the set of all possible suffixes as being a sort of tree that grows exponentially. For some depth, all suffixes that have depth less than that will be accepted by both states. But at some point, they'll branch off. And so here, in red, we're showing suffixes that are accepted only by one state, but not by the other. And so the boundary is this green line. It's the minimal set of suffixes that are accepted continuing from one state and not from the other. And so this implies a new test for assessing world model recovery. And the test is as follows. Rather than just looking at a transformer's predicted next token, we should look at the K next tokens. We should look at enough tokens that allow us to differentiate between states. And crucially, K isn't fixed. K isn't always 1, it's not always 10. K depends on the two states that we're trying to differentiate. For some states, it might be 1. For some states, it might be very large, but it's always going to be some finite number. So we're gonna implement two kind of versions of this test. The first we call this distinction test, and it works like this. We first take two sequences, S1 and S2, that lead to distinct states Q1 and Q2 in the underlying DFA. So we can use these two sequences or these two states to calculate the model's the true Myhill-Nerode boundary, which we're calling MNB, for the DFA. So this object MNB Q1, Q2 will tell you the set of suffixes that are legal for Q1 and not for Q2, or vice versa. We can also do the same thing for the generative model with one small caveat. The generative model, of course, is not a function of states, it's a function of sequences. So we're gonna define an analogous boundary for the model based on the two sequences that led to those two states, S1 and S2. So we now have two boundaries, one for the DFA and one for the model. And the test is simply how similar are the two boundaries, the one for the model and the one for the DFA. And so, in this chart here, we're having the true boundary in the DFA is green, while perhaps the model's boundary is in this light pink color. And there are a bunch of different ways we can measure how similar these two boundaries are. In the paper, in this talk, we're just going to focus on two metrics, precision and recall, which just measure how much of the boundary is being captured by the model and how much of the model's prediction of the boundary is actually part of the true boundary. And so we use these two metrics because, sort of like in binary classification, there is a trade-off between precision and recall with our threshold parameter. So as we define what it means for a model to accept a sequence, as we vary that definition, these two metrics will vary as well. And the other metric is something that we call compression, which is in some sense a special case of distinction. Here we again take two distinct sequences, S1 and S2, but they now lead to the same state Q. So, for example, this could mean, two Othello openings that result in the same board. You could have two different sets of moves, but still after those same set of 10 or 15 or 20 moves, the two boards could look the exact same. And so when we have two sequences that lead to the same state, the DFA, of course, has no Myhill-Nerode boundary. All sequences that are legal after S1 will also be legal after S2 and vice versa because they correspond to the same state Q. So then the test is just assessing whether a generative model recognizes this boundary. If a generative model has a boundary, if it thinks that some suffix is legal after one prefix and not the other, then it has failed to realize that these two distinct prefixes actually correspond to the same state. So we have these two tests for comparing a model's Myhill-Nerode boundary to the true boundary. Compression assesses whether a model has understood that two prefixes are equivalent, and distinction assesses whether a model's differentiation between two states is the correct differentiation. So both of these metrics are well defined, but they're intractable to compute over all pairs of states and prefixes. So in practice, these metrics will depend on how the test is implemented, specifically how states and prefixes are sampled and how we define model acceptance. So throughout this talk in the paper, we're going to sample pairs of states uniformly at random and approximate prefix sampling uniformly at random conditional on states. And we'll also consider different definitions for how acceptance is defined by varying thresholds and thinking about input-dependent thresholds such as top P sampling. And so, like I mentioned in the previous slide, what varying the threshold does is it improves precision at the expense of recall or vice versa, which is why we measure both. So, but before I move on, I want to draw connections to some related literature, some of which I think has been presented in this group. A fairly large literature has studied which formal languages can be theoretically expressed by different classes of generative models, such as RNNs, LSTMs, transformers, and state space models. Also very related, there has been work that's shown that transformers can learn shortcuts to DFAs and do so when trained with state supervision. So in contrast, we're not studying structural capabilities or trying to assess whether models trained on state can learn state. We're instead interested in asking whether models trained on next token prediction can recover state and how that could be measured. And so this also relates to a fairly large literature that sort of sprung up trying to assess the world model capabilities of large language models. It studied scenarios like games and logic and spatial grids. And so these are all examples of DFAs. And we propose metrics for DFAs generally, and we will then apply them to some of these examples. So, with that, I want to start by I want to focus now on one illustration, which covers taxi rides in Manhattan. So we have a data set of 12 million taxi rides taken in Manhattan in 2014. The figure on the left sort of shows a heat map for the common taxi rides. So what we do is we turn every taxi ride into a sequence. And the sequence starts with an ID for the starting intersection, an ID for the ending intersection, and then a set of directions that get you from that start intersection to the end intersection. And so what these directions are is each token is one of 8 cardinal directions, northeast, northeast, south, southwest, etc. And it corresponds to, as someone traversing the graph that corresponds to Manhattan and getting from the start node to the end node. And so we do this for every taxi ride, which gives us, many, many sequences. And these sequences obey a true DFA, which roughly corresponds to the graph of Manhattan. Every node is an intersection, and the transitions correspond to the directions of the roads that connect intersections. So with this example, we're interested in asking whether a transformer trained on sequences does it uncover the true world model, which in this case is a map of Manhattan. So we're going to train 3 different kinds of models. One model is trained on just using an API to get the actual shortest graph traversals for each ride. We're going to also consider a few other conditions. In one, we're going to simulate traffic by adding noise to some of the edges and taking the shortest paths. And in this example, we now have multiple ways to get from path A to path B. And we're also going to consider a sort of a random walk setting, where we're going to sample a starting node uniformly at random, randomly sample direct traversal directions among the set of possible directions uniformly at random until we randomly stop, and that is our traversal for random paths. So for each of these models, we create train and eval sets, making sure that if for every origin destination pair in the eval set, we make sure that it doesn't appear in the training set. So the eval set contains new origin destination pairs. And we're going to train models following the GPT-2 architecture for each model, or for each kind of training data. And so we can start by just evaluating each model on held out data. And so the first thing that we do is we evaluate models on the next token test, which is we assess what predictions, given a traversal so far, we prompt each model, we get each model's predicted next token and see if it's a legal term. And the models do quite well. They get close to 100%. But it's important to point out that no model gets exactly 100%. So they always do make some errors on the next token test. We also consider looking at the transformer's representation. We train a probe to predict the current intersection implied by the ride, and it does quite well, above 90% accuracy for the 3 examples. And the model can even generate shortest paths out of sample. It's more than 90% of origin destination pairs in the eval set. When we give it to the shortest paths model, it generates a traversal that takes you from the origin to the destination. So this, in some sense, this is really impressive results. This is saying that in some sense we've taken just a list of passively collected traversals and uncovered something that you can imagine looks something like a navigator. It can tell you for these sets of origins and destinations how to get from point A to point B. But how do they do on the proposed world model metrics? Well, these tell quite a different story, where the first column here is compression, and the next 2 columns here are for our precision recall for prefix should also be legal after the other. The shortest paths models get less than 20% for each, and while the random walks model does better, it still misses out on a third of the state comparison. And so distinction is a similar story for the shortest paths models. Um, they score between 25 to 35%, while the random walks model does seem to at least be able to distinguish states, random states quite well. So, you may ask, why should we care about these world model metrics? Besides, I just showed you that the model can find shortest paths out of sample. And so if you just want to use the model to find, these shortest paths, then in some sense we should be satisfied. We can just use the model. Well, the reason that I think it's important to care about these metrics is that not having the right world model means that a model could do badly on different, but subtly different but related tasks to models that it does quite well on. And so an example of this is detours, where you can imagine a task related to shortest paths, where we want to generate traversals from a model, but artificially introduce detours. And so we do this by sampling paths from a model as before, but adding detours. And by adding detours, I just mean that we take a model's generated next token and replace it with some other valid token that would also get you from the origin to the destination. And so we consider two ways of adding detours. One is we just replace the generated tokens randomly with another valid token. The other, we adversarially select tokens to provide the token that the model would assign the lowest likelihood to that still happens to be legal. And for both of these, we find that performance degrades, quite quickly. So while the shortest paths model can get close to 100% traversal accuracy when there are no detours, it drops to 67% when 1% of the steps have detours, and that also drops, and it drops even more to 9% when there are 10% of detours. And we see a similar thing for the noisy shortest paths. Random walks does do quite a bit better, but its performance eventually degrades as well. And so here, I want to point out too that the performance on these detours, it correlates quite strongly with these models' performances on our metrics. Now, so you may ask how bad are these world model failures? Are these small failures or are these large failures? And to answer this, we attempt to visualize the implicit world model that the transformer learns. And we can do this because in the setting where we're training a model to provide traversals through New York, we have a nice way of visualizing the true world model and any implicit world model, which is that an implicit world model here is some latent graph that the model believes that the model is obeying. So we can so answering this question involves reconstructing the graph of New York that each model believes is correct. And so, there are a few different ways to do this. We do this we try a few different graph reconstruction algorithms, where each one of them involves generating sequences from a transformer, and then we very generously assume that the model knows the true locations of intersections, which is of course a very, very generous assumption. And then we ask what roads must exist for the generated sequences to be valid. What is the true graph that obeys all of the sequences that are generated by the transformer? And so we implement this essentially with a greedy algorithm where we're given the nodes and we reconstruct real roads or edges from each step of the sequence until forced to do otherwise. And we also consider adding some constraints, such as every node has at most 4 roads that lead to it, which is the true which is happens for the true map of Manhattan. And we consider these to boost the performance of these models, to really be very generous to the models. So as a first sanity check, we generate data from the true world model. So these are all true sequences of traversals in Manhattan. And by construction, as we'd expect, the reconstructed map is exactly the true map of New York. We consider another sanity check, where we generate data from the true world model, but add noise such that it makes errors at the same rates that the transformer makes errors. And so when we do this, we get this map, where we have a reconstructed map, That's imperfect, but at least it's sensible. And so one way to think about this is what would happen if the transformer, was always outputting the true world model, but just sort of made kind of like independent transcription errors every now and then. So now, given all this, we can reconstruct the transformers map from the true sequences. And this is what we find. It's a Frankenstein map of New York. It sees, there are all these edges that don't exist. There are, flyovers. It assumes many, directions, then curving edges that go from, intersections that just do not connect. It really does not seem to have structure resembling New York at all. And the only reason that it even sort of we can visually make out Manhattan is because of all the generosity we've given in terms of mapping each intersection to the correct physical locations and trying to minimize wrong roads and flyovers in our graph reconstruction. So, the same model can perform well on out-of-sample generation, but have a completely nonsensical world model. And you may ask, how can we reconcile these two things? So one way that I like to think about this is what Leo Breiman calls the Rashomon effect, which has been mostly studied for supervised learning methods. And this effect refers to the fact that two models can perform similarly with very different mechanisms. So in our case, we're applying it to large language models. It refers to models being near perfect on some metrics. So it looks like the true world model if you just look at some metrics, but its errors reveal incoherence that's far from the true world model. So we consider another test case too, where we also look at Othello. And there are two ways that we can generate sequences from Othello. One is called championship games, where we look at actual games of Othello that people played in championship tournaments. And the other is in synthetic games, where we randomly generate games, just simulating using a computer. And so prior work has found that models trained on both kinds of sequences do well on these next token and probe tests. And so we now consider applying our metrics to model to transformers trained on both of these sequences. And we find our metrics find a distinction between these two types of Othello games. We find that while the model trained on championship Othello does quite poorly, the model trained on synthetic Othello does quite well across these metrics. And this distinction is borne out on a detours exercise, where we run a similar detours exercise to the one that we ran for maps, where a detour here is we're replacing a transformer's predicted move in Othello with some other valid move. And while we find that performance degrades quickly for the model trained on true games, it remains quite high for the synthetic model, regardless of what percent of detours we add. And so a couple notes here. One is that there's a resemblance here to the map setting in the sense that for both of these, the model trained on synthetic data, on just randomly generate data that covers the full support, does better than models trained on championship real world games. And this is intuitive because if you're training a model on championship Othello matches, it sort of becomes impossible to distinguish what's a very, very bad move such that a championship player would never play it, and what's an illegal move. In some sense, it's impossible if it's not in the support. So we have one more test case where we look at logic puzzles. And we essentially give different actual large language models different logic puzzles that involve individuals seated around a table. And the model sort of has to figure out where each individual is seating. And so here, as we generate each statement, we can think of a DFA as the set of all possible configurations for each statement so far. So before we have any statement, the set of possible states is all possible seating positions. And as we add more seating positions, the state space narrows. So one way to test compression here is that we can prompt large language models with two different ways to reach the same set of possible seating configurations. So here, context one and context two, they're both different. They're different statements, but the set of possible seating configurations under both of these. And then so to test compression, we can query models and ask, does it recognize or does it produce the same predicted possible seating arrangements for each context? And so that's what we do. The column on the left, it shows that when we have given models all possible, statements and such that the state space is narrowed down to a single seating arrangement, they do quite well. But when we measure compression, as in the last slide, along with distinction, these models perform quite poorly. GPT-4 only gets 21%, gets only 21% compression precision. And so I think it's very interesting that these models can do quite well at predicting who is in what seat when the seating arrangement is fully specified, but they perform so poorly at understanding that or at making the same predictions, for example, when two contexts should result in the same set of states. So, to wrap up, in what have we done? We've proposed metrics for evaluating the implicit world models in generative models. And we have used the Myhill-Nerode theorem from language theory to motivate tests for assessing how models perform on boundaries between two states that can contain many tokens rather than single next tokens. And so across applications, we found first that transformers can do amazing things with completely incoherent world models. We saw this for maps that transformers can essentially replicate some of the functionalities of Google Maps or Waze. But at the same time, this incoherence made them fragile for other tasks, such as when we added detours. And zooming out, bigger picture, this sort of incoherence is a problem whenever we hope to use a generative model like a transformer to learn something about the world, which is sort of one of the goals of using transformers in the natural sciences in settings like chemistry or genetics. So I want to just conclude by mentioning a couple of limitations and next steps that I'm excited about. One is that our tests are only applicable to true world models, to when the true world model is a DFA. And of course, there are much more complicated possible world models. So I'd be interested in extending this to these more complicated worlds. I suspect that the ideas of compression and distinction will also be useful in these other settings, but the actual implementation of the test will probably have to be quite different. So another point is that for our metrics to be calculated, the true world model has to be known. And in many cases, the true world model will be unknown. We a lot of times we care about getting world models, about seeing a transformer's world model if we don't actually use a world model. And so, while these test beds will be limiting for this case, like I still think they're useful for improving models. What can we say about an LLM's world model if it can't even recover a map? But there are more realistic and I think also interesting extensions, such as when the world model is possibly known. You can imagine a DFA where the states are known but not the transitions, or vice versa. And extending these ideas to that setting is something that I'm also interested in. So, with that, I'll wrap up. Here's a link to our GitHub. So thank you all for coming.